Today we're talking about biometrics. Biometrics are an example of what you do or what you are. So a biometric is a measurement of a physical characteristic. And examples of biometrics are your fingerprints, your hand geometry, maybe retina measurement or iris scan, your voice or facial features. These are all biometrics that can be measured, physical characteristics that can be measured and used for authentication. There are others, such as gait or typing rhythm and mouse patterns, that have been explored as well. And those are not biometrics per se. They are based on what you do, your behavioral characteristics, rather than what you are, your physical characteristics, but still the general idea is the same. And we think of biometrics as being new inventions. The use of biometrics for authentication we think of as being new, but actually the use of biometrics for authentication predates computer technology. Certainly handwriting, a signature on a piece of paper, that's an example of using biometrics for authentication. Voice recognition, we just naturally use the sound of someone's voice to recognize who they are. Fingerprints, the use of fingerprints predates computer technology. Even if you think of shibboleths, right? These fall into the category of a behavioral characteristic that dates back centuries. So the registration process when you're using a biometric looks like this. A physical measurement is taken. So there's some sensing device, maybe a fingerprint reader, maybe a camera, some sensing device that takes a physical measurement of the person. This physical measurement must then be digitized and features are extracted from the digital representation of the physical measurement. And the set of features that are extracted are often called the template. So the template is extracted from the sensed data. So from a picture of someone's face, a numeric representation of the salient features might be the distance between the eyes, the placement relative, the nose, eyebrow, eye, and ear placement, and how they are relative to each other. Those are things that might be digitized and extracted as features. And then the user's name that has been provided during registration, along with this extracted digital template, is then passed along to the database. So the physical measurement is not passed along or stored in the database. The picture of the person's face is not passed along and stored. One issue that arises with the use of biometrics is that of failure to enroll. And a failure to enroll happens when the sensing mechanism is unable to capture an adequate sample. And it could be that any one of the sensing mechanism or digitization or feature extraction, any one of these things can fail, and the result is failure to enroll. And we can talk about what is the failure to enroll rate for a particular biometric mechanism. So this is the percentage of users who cannot successfully register, or the percentage of registration attempts that are unsuccessful. Assuming you have successfully registered, down the line you want to use your biometric to authenticate, you want to gain access to your account. The authentication phase looks like this. The user presents whatever it is, their fingerprint, their face, to be measured again. The user has to interact with the sensor. A physical measurement is taken. The physical measurement is digitized, features are extracted. The ID, the user's name, is sent to the database and queried. The database returns the stored template, the digital features associated with that ID, and then a comparison happens. The measured features compared to the stored features to see if there's a match. And here we have to worry about failure to capture. And this, again, could be any one of sensing, digitization, or feature extraction that can go awry. And this is analogous to failure to enroll, but refers to a failure during authentication rather than during registration. And again, we can talk about the failure to capture rate, the percentage of authentication attempts that are unsuccessful. The other more serious challenge for verification is the comparison or the matching stage. In practice, the two set of features will never be exactly the same. Biometrics change from day to day and in different environments. Measurements are never perfectly accurate. Different sensors will produce slightly different measurements. So for example, your fingerprints are affected by how much moisture you have in your hand, any calluses in your hand. In practice, multiple samples are taken, but even still, it's never going to be an exact match. The way that you have with passwords, right? A password will always produce an exact match, but with biometrics, that's not the case. So instead, a threshold is chosen. If the two templates are close enough, it is deemed a match. Otherwise, it is not. But sometimes the wrong decision can be made. And in that case, you have to worry about false positives and false negatives. With false negatives, it is the case that the user is the identified user. So the person who is presenting and trying to authenticate is the identified user, but their biometric is not considered a match. And that's called a false negative. A false positive is when the user who has identified themselves and is trying to authenticate as a valid user is considered a match, but is not actually the valid user. That's called a false positive. And you can ask, which is better? There's always a trade-off to make. Because we're not looking at exact matches, there's always going to be a trade-off. There will be some false positives and some false negatives. You can improve the false positive rate by, but that will make the false negative rate worse. And so there's a trade-off. And you might ask, which is better? Is it better to have a high false positive rate and a low false negative rate, or vice versa? And there's no one answer, right? You're asking, is it better to never let an imposter pass authentication, or is it better to never block a legitimate user? And the cost of a false positive is a security risk, right? Maybe you let an imposter pass when you should not have. The cost of a false negative is a usability risk. There's someone who should have access to the system who is denied access, right? There's a loss of availability. And this is a policy decision. There's no one right answer. And the answer varies for different situations and different systems. And we see this even in our, in the physical world when you're not on a computer system. So when we think about criminal convictions, wrongly convicting someone and sending someone to jail versus letting someone go free, we might want to make a different trade-off there compared to voting, wrongly letting someone voting versus denying access to the vote, right? So what are the trade-offs that we want to make? With computer systems, sometimes when we're talking about network traffic or a basic login system, an acceptable false positive rate that we often talk about is maybe a false negative rate of 1% is acceptable, but a false positive rate of 0.001% might be acceptable. But again, these numbers can vary from system to system. Okay, so for authentication, we look for scores that fall within Alice's range rather than for a particular match. And so to do that, we look at the probability density function. This defines the probability for any range of values that the variable being considered, in this case, the template score, is in that range. So in this case, the variable is the template score. This is a single number used to represent the digitized features of, for example, the fingerprint. The area under the curve for any interval, so the integral of the probability density function, represents the probability that the variable, the template score, falls within that interval. You can think of probability density functions as being analogous to a histogram, right? It's akin to a histogram. Probability density functions are used with continuous variables, though, rather than with discrete variables. And the reason we need this is because, for a discrete random variable, the probability of the random variable being a value is meaningful. So if your random variable is a coin flip, right? Will your coin be heads or tails? The probability of your coin being heads is meaningful. Or if you're talking about rolling a die, the probability of it landing on a 1 is meaningful. But for a continuous random variable, where you're not talking about, for example, integers, but you're talking about real numbers. So a continuous random variable, the probability of the random variable being a discrete value, for example, the value 1, is always 0. Rather, the probability of its being within a range is what is meaningful. So again, the probability density function is akin to a histogram, but for continuous variables. The area, in a histogram, the area of each rectangle equals the relative frequency of the corresponding class of values. And here, the area under the curve within a range defines the probabilities. The area under the entire curve is equal to 1. Okay, so we know we're using probability density functions, but now we can see that Alice's range and Bob's range overlap. And if we accept any value that falls within Alice's range, there's a chance it will also fall within Bob's range as well. That means that Bob could present himself as Alice and potentially be authenticated. So here you can see this is where false positives are possible. So we set a threshold. Only template scores that fall above the threshold are accepted. But there's a trade-off to make here. The shaded in area shows the probability that Bob can successfully authenticate as Alice. This is the probability that Bob's template score will fall in the range above the threshold that is set for accepting Alice's template score. This is the chance for false positives to occur. And here we have the chance for false negatives to occur. The probability that Alice's measurements will fall below the threshold set for her template score to be accepted, and Alice will be denied access to her own account. There is always a trade-off between false negatives and false positives. Let's turn our attention to the usability of biometrics. Biometrics are, in general, considered usable. There's a low cognitive load for the user. Users don't have to remember long or difficult passwords. They also don't have to carry any extra hardware around with them. It's easy to use. For example, rather than typing in a long password on a phone keyboard, which can be difficult to do, the user just presents their finger for fingerprint sensing. And it scales well for users as well. Users don't have to remember different passwords for different accounts. In other words, the burden does not increase with the number of accounts. These reasons make biometrics appealing for users. Biometric-based authentication schemes are appealing for users. On the other hand, there are some issues with usability. For example, failure to enroll, failure to capture, and false negatives can all lead to valid users being denied access to their account, a violation of availability. It's also the case that some users may be hesitant to accept the use of biometrics out of privacy concerns. They don't want the system to have, whatever the system is, they don't want that system to have their fingerprint information, for example, or their facial recognition features, for example. So that's the usability of biometrics. Now let's talk about the security of biometrics. On the one hand, your physical characteristics are unique, and so that would seem to make biometrics secure. No one else has your fingerprints, no one else shares your particular face, and so physical characteristics are unique. However, your physical characteristics are not secret. And remember, we said at the beginning that things that are used for authentication really should be secret or private. But for example, you leave your fingerprints all over the place. Every place you go, you leave your fingerprints. Your face and pictures of your face are all over the internet, most likely. And this, the lack of secrecy or privacy of your physical characteristics, makes the use of biometrics insecure in a remote or an unsupervised setting. So let's look at what happens in a remote setting when biometrics are used for remote authentication. And so this is the case where the user is logging into not their own phone, for example, using a fingerprint, but some remote server across the internet. Here, because the login is happening remotely, there's no requirement that there's actually a physical measurement taking place at all. So the user might be able to just steal a measurement from some other database, from some compromised database, steal the stored template, the stored credentials, and just reuse them. No sensing, no digitization is taking place here. No feature extraction is taking place. Remember, the sensing and digitization happen where the user is. Biometrics are considered secure because even though they're not secret, it is assumed that they are physically tied to the person. But in remote authentication settings, that need not be the case, and there's no way to tell that any sensing took place or did not take place. So let's say now that we move to a local setting, so this is not remote authentication, this is a local setting, local authentication, but an unsupervised authentication. So the attacker does have to interact with the sensor, but there's no one there checking to make sure that the attacker is actually interacting with the sensor. And in this case, the attacker may be able to spoof the physical characteristic being measured. For example, laptops use facial recognition. Some laptops now use facial recognition in order to let you log into your laptop, right? In order to let you gain access to your laptop. The way this facial recognition works is that the user has to interact with the sensor, but for example, instead of putting their face in front of the camera, the attacker can put a picture of someone's face in front of the camera. And that might be enough to trick the camera into thinking the actual user, the real user, the correct user is in front of the camera, even though it's just a picture of the person. And so, here we see an example of the cat and mouse game that can happen. So attackers or researchers actually first demonstrated that this was a viable attack against the facial recognition features in your laptop. And so the defense against that was to require some maybe movement of the picture. So it's not enough for a static picture. The camera, the sensor sensed the picture, took a picture, but also had to sense some movement. And if the camera did not sense any movement, then would not accept the measurement, the sensed measurement. And so this was a good defense against just putting up a piece of paper with a picture. But then, the countermeasure to that, the attackers were able to, then the next step was the attackers took a picture, cut eye holes out of the picture, held the picture up in front of their face, in front of the attacker's face, and their eyes would move, they would blink their eyes a few times, and that was enough movement to fool the sensor. So the next countermeasure to that was that the sensor had to sense some heat. So a cold piece of paper with some movement from the eyes was not enough. There needed to be some heat generated. And again, the researchers were able to demonstrate that it's easy to attack this as well by just adding a heat source, right? And so that was easy to thwart. The most recent mitigation is that actually the sensor is now trying to sense a 3D person, right? And so it has to be a person, a face that is not flat, not two-dimensional, a picture, but something that is actually three-dimensional, has movement, and has heat. However, again, researchers were able to thwart this. And what they did was, for a particular target, and in this case, this was researchers demonstrating the attack, so they used one of themselves as the target. They went to all of the publicly available pictures of that person, of the victim, which was, one of themselves, all the publicly available pictures online, and there are tons of them for most people. They used those pictures to build a 3D replica of their face. So there were enough different pictures that they could reconstruct the face and use a 3D printer to build the face. Again, add some movement, add some heat, and this was enough to spoof the sensor. And because we're talking about unsupervised authentication, there's no guard there watching to make sure that there's, that a person is sitting in front of the camera and there isn't all of this other, the attacker is not trying to do something with a model or a 3D printed face. This is why, for example, if you have to provide your fingerprints or handprint to gain access to a building, you should always have to do it in the presence of a guard or a person there, right? If there's a fingerprint sensor or handprint sensor that allows access to a building and there's no one standing guard to make sure that a real person is doing it, it's possible to spoof the measurement. Okay, so when we're talking about the security of biometrics for user authentication, it turns out that biometrics are not secure for use in remote or unsupervised settings, even though we do see them used that way. It's also the case that they cannot be revoked easily, right? And so once compromised, there's not much you can do. You don't have a lot of different fingerprints you can use. Maybe you can use one of your other fingerprints, but eventually you run out of fingerprints. And there is also the issue of false positives that can occur, which will weaken security. So if we want to summarize biometrics as a means of authentication, we can say that they are easy to use and provide a low cognitive burden to the user, which makes them attractive. But it turns out that security is lower than expected, and users do have concerns about privacy.